And it's Tuesday afternoon, and we all know what happens. Yes, we've got creationministries.com, or it's Creation Ministries International, and they have a website called creation.com. That's better. And today we have a very special guest, Scot Devlin, who I haven't talked to for, how long is it, Scot?
I don't know, it feels like it must be a year at least, Nick.
Yeah, it's been a while.
Yeah.
Well, welcome.
Yeah,
You there?
Thanks, Nick. Yeah.
Yep.
Yeah, I'm here. Can you hear me okay?
Yep, we've got a little bit of a delay, I think. But look, great to have you, Scot. And, of course, for those who don't know who Scot is, you can tell by his accent he was born in the UK. And Scot has ministered in countries like the United Kingdom, France, Italy, Switzerland, Canada, Mexico, New Zealand, Australia, Kenya, Mozambique, South Africa, India, Nepal, and Brazil. Wow, that's like all over the world, right?
Yeah, I think that's been quite stationary the last 7 or 8 years here in Australia, relatively. But before that was in a lot of different places.
Yes. Now, you were sponsored by Royal Dutch Shell to you did a degree in geophysics at University of Leeds. Now that's in England, isn't it?
That's right. Yeah.
Yes. And, of course, geophysics. Can you explain geophysics a little bit to me, Scot?
Yeah, the way I explain it is, most simply, is it's the physics of the Earth. So you've got geo, which is Earth, and then physics. So it's the physics of the Earth. So we look to see what's inside the Earth, and that can be at all sorts of different depths. In the people that are more into the research side of geophysics will be looking maybe at earthquakes and volcanoes and thinking about those type of things and looking at these earthquakes happen deep under the ground. But then you can go to a more shallow scale where we look for oil. So one of the main industry applications of geophysics will be the oil industry. So a lot of geophysicists end up working for the oil industry. And then we can look even shallower than that. So before you're building foundations for a large building, skyscraper or a road or something like that, often you need to do some geophysics as part of the site investigation. So it's just anything that's related to looking inside the Earth or the physics of the Earth. So I guess if you know the physics of the Earth, you know that when you send down, whether it's a sound beam or an electromagnetic signal or you put an electric current in the ground, you know you can interpret the signals you receive back and therefore decide, okay, this is what's under the ground and this is roughly where it is. And of course, that's the idea with oil exploration. You've got to find out where the oil is, and when you're looking at earthquakes and you're tracking them around the world, you're looking where was the epicenter, where's the focus of the earthquake, and where does that travel to?
Yeah. So being somebody who's pretty much an expert in looking at the inside of the earth, which is sort of like Dr. John, but he looks at the inside of people. And so for someone who looks at the inside of the earth, we often see things like, particularly here on the Central Coast of New South Wales, we can drive down to the Hawkesbury River on our way to Sydney, and we see these giant layers in the sandstone where they've cut the freeway out. And, we've been told numerous times that those layers are layers of sediment from the Great Flood. Now, you looking at the earth, you've seen many mountains, and you were just sort of talking about, where the plates push together and they form mountains. We hear stories from people that say, oh yeah, look, I believe the earth is billions of years old. And those tectonic plates that are pushing together are just sort of constantly always folding over and over, and that's why we start seeing dinosaurs now and their bones coming up now, because they really were around there that long ago, but now it's sort of the second time round. What would you say to those people?
Yeah, so first of all, you'd try and lay the groundwork that when you're interpreting, first of all, you might say, well, do those dinosaur bones come with the tag on saying that they are 65 plus million years old? And the answer, of course, is no. Well, how did you get that answer? Well, it was through looking at the layers of the ground and having a interpretation that they're millions of years old, and then seeing, well, okay, we find dinosaur bones in this layer and in the Triassic, Jurassic, that era, and so we say, well, okay, because they're in those particular layers of the ground, we'll assign them this age. So you've got to think, well, how did those layers get that age to start with? Well, there was a assumption that went in, and in this assumption, we call it uniformitarianism. It's actually named by, there was a geologist, James Hutton, that came up with this philosophy about 200 years ago. And he said, well, look, all the things that you see going on today, the processes you see going on today, the erosion that you see happening in river channels and the rate that you see sediment depositing today, that rate has always been going on for a long time in the past. And if you use that assumption, then when you see big layers of sediment, then you would conclude that they were laid down a long time ago in the past, because the rate of sedimentation today is very, very small. On the bottom of oceans, you're just talking centimeters per year, less than that, millimeters per year of sedimentation. And so when you see kilometers sediment and you interpret them as being millions of years old, but of course you alluded to it, if you have a worldview that includes a flood that could easily deposit a lot of sediment at once because of the size of the flood, then the age, when you look at the rocks, you see a different age. And that's really the key point to this whole creation-evolution debate.
Yeah. Now, Scott, understanding how these giant tectonic plates work, like I've seen pictures where they show one plate goes underneath another plate. Is that correct?
Yes. So that would be what you call a destructive fault. And yes, some go underneath each other, some will. And it depends on the density of the plates that are crashing together. So we've known since, it's only really since the 1970s that people have been confident that this process of plate tectonics is even a thing. And of course, 80s and 90s brought about a better technology in GPS, and now we can track the plates moving, and they move very slowly at the rate of maybe centimeters per year. And so what you're talking about there is a destructive plate margin, and that's when you have the more dense tectonic plate of like an oceanic lithosphere. So you have the ocean will be, or the ground below the ocean. So the plate below the ocean is generally more dense than the continental plates. So the plates that make up the Earth. And those oceanic plates, when they crash into a continental plate, because the plate is more dense, it will subduct. It will dive under the other, like you're describing. And that's what we call a destructive plate margin. And that can be where you find the focus of many large earthquakes. But if a continent and a continent collide together, then instead of one diving under the other, what you'll have is both of them will crumple and crush up. And an example of that is the Himalayas today. Even the Himalayas is actually rising. I think it's on the order of centimeters per year. It's rising at the moment. So we can see the aftermath of the flood even in the Himalayas rising, because those plates are still crashing together and still rising.
With the Himalayas and areas like that, though, do you get many like dinosaur bones found where there's been so much action, so much movement, as opposed to like the valley of the whales, where all those whale sort of bones are? It seems to be in an area that doesn't have a lot of movement. Can you find them anywhere, or is it more common to find them in less active areas?
Yeah, that's a really good question, Mick, because the answer is no, you're not going to find any type of fossils in a volcanic active area. Because if you think about the type of heat that is in the magma and generated in volcanic areas, it's enough to obliterate the fossils. So you find fossils only in sedimentary rocks. And people might remember from school geology or school geography that there's three types of rocks. You've got sedimentary rocks, and you've got metamorphic rocks, and you've got volcanic rocks. So volcanic and metamorphic rocks, the type of heat that's involved in making those type of rocks is way too high for fossils to remain. So it must be in sedimentary rocks. And actually making a fossil is a very interesting and a very difficult thing. Some people think, well, if something dies, it becomes a fossil. And that's, it can happen, but it's very difficult for the fossil to happen. And actually you need a very specific set of conditions to form a fossil. Yep. Namely, you need a lot of sedimentary rock, and you need it to bury, especially if you see these intact fossils. So people might be used to seeing maybe a fish fossil, and it's fully, you can see the full bone structure of the fish. Yep. Well, that fish wouldn't have died by natural causes over millions of years, because otherwise those bones would have scattered. And I often ask people this in audiences, I say, as we speak in various different venues, I say, does anyone keep fish here? One or two people might raise their hands, and I'll ask the question, when your fish dies, what happens to it? Does it sink? And they say, no, it floats. And so often when an animal that has cavities in it dies, then some of the bacterial decay can cause the gases to inflate that particular animal, and it will float to the surface. I say, well, what? And if you imagine a fish floating, well, it often gets picked off by seagulls. And then I put the question a bit wider and say, look, has anyone been snorkeling before at the beach, or has anyone been swimming at the beach and looked at the bottom? And of course, most people have done that. I asked them, do you see any fish waiting at the bottom of the seabed, waiting to be buried, to become a fossil? And they say, no, of course, the seabed's very clean. And so this is really a chink in the armor of the secular evolutionary worldview is, well, how do you form fossils anyway? And a lot of them are starting to admit, well, I mean, a lot of the scenarios that you'll read about, you might read about, say, a new dinosaur grave that's been found, and you'll find out, there was a big flood and the dinosaurs got buried quickly, because really that's the only way you can bury a fossil. If you're going to make a fossil, you need to bury it very quickly so all the bones stay intact, and you need to bury it with a decent depth of sediment. It has to be really deep, and in fact, even the biggest tsunamis we see today only release about 10 centimeters of sediment, which isn't really sufficient to make to fossilize even a fish, so let alone a T-Rex or something like that. So this is a really interesting point. That it's great if people can grasp a hold of it. How do fossils form? And if someone wants to look more into that, they could check our website, creation.com, just in the search bar, how do fossils form? That's a really key thing to understand in creation evolution discussions.
And I guess the other thing is a fossil could not have followed one tectonic plate down below another one and been there for a few million years and then literally come back up again. By the sounds of it, there's too much action, too much heat. It wouldn't survive.
Yeah, exactly. Yeah, sorry. Get back to your main question, that's correct. That any kind of where you've seen a lot of movement in the past, where you have igneous rocks, you're not going to find fossils in igneous rocks. It's not possible. But in the sedimentary rocks, in certain parts, we find a lot of fossils. There's millions and millions around the world. So the question, how did they get there, is a very good question.
Absolutely. You are on 94.9. We have Scot Devlin on the line from Creation Ministries International. Now, I mentioned earlier all the amazing things that Scot has studied. He was just telling me in the break that he has a bit of an interest in astrophysics, which is amazing. And Scot, I saw a story that you wrote a few years ago, and it was before they'd actually launched the James Webb Space Telescope. Now, of course, we've all seen images from the James Webb Space Telescope since then, because the media has sort of looked at them and gone, wow, they're the most amazing things I've ever seen. I remember when I saw them, I thought they are just, it's like artistic. God had a great day when he did those. They look absolutely awesome. All the, I don't even know, they're just star constellations, all that sort of stuff. And of course, they seem to be looking at things from further away than they ever have before. And we've realised how much better this James Webb Space Telescope is than we ever thought it would be. And the story you wrote was, will the James Webb Space Telescope find extraterrestrial life? And so I was hoping you could tell us about all the aliens it's found.
As we predicted in the article, and as has materialised, it hasn't found any aliens. And I could go a lot further than that. It actually hasn't found any habitable planets. And there's this term, but yes, I should, before I go into detail with that, I should say it has, as you said, it's produced some fantastic pictures. And it is a big step up for us from the Hubble Space Telescope, which was a huge step up as well. And a lot of people might remember the Hubble Space Telescope. Well, it's still in operation today, the Hubble Space Telescope. And that was very famous because when it first went up, they had one of the mirrors slightly misaligned. And so they were, the pictures weren't in focus at the beginning. So this multi-billion-dollar project went up into space and the pictures were not in focus, which meant it was useless. And so they had one of the old space shuttle programs And this was in the late 90s, I believe. One of the old space shuttles that we used to see NASA fly up that, look a bit like a plane and then fly up to space.
Yep.
They had to send one of them up with some astronauts to fix the mirror. And of course, that was very good once they fixed it, because it brought back the deepest images of the universe we've ever seen. And so the Hubble Space Telescope's very famous because of its abilities. But now we've got this successor, the James Webb Space Telescope. Of course, with this one, it was a nail-biting launch because they were not able, because they've sent it to this point they call L2 in space, and so it orbits, I think it's 1.5 million kilometers away from the Earth. So it was so it's a lot further away than the Hubble Space Telescope. Yep. When they launched it, there was everyone knew there was no hope. If we get it wrong, there's no hope of correcting it, because we can't visit it, unlike the Hubble Space Telescope, which only orbited about 500 kilometers from the Earth's surface.
Yeah. But you say that they've found nothing really that points at life or even a habitable type planet.
No, yeah, and I kind of predicted that in the article, and it was quite an easy prediction because, having said that, from a biblical point of view, it's quite an easy prediction because, we believe that God made the earth very special. It says the heavens declare the glory of God, and so space is completely vast, and there's incredible pictures, as you say, that we see back from the James Webb Space Telescope and its preceded the Hubble Space Telescope. But so the images are fantastic, and we find that these very interesting stars and worlds up there, but none of them are like the Earth. We find, big gaseous stars. It's just when you think about our star, that's just a big ball of gas burning. And some of these exoplanets we find are dry and barren. We find nothing like the Earth that has water on the surface, separate land masses. There's just some incredible design features of the Earth that we found nothing like. But you probably wouldn't get that impression if you read a lot of the news articles. You'd probably get the impression that we've probably even found Earth 2.0. In fact, I haven't been able to count the number of articles that I've said, we've found the Earth 2.0. But that's not quite correct when you look into it. I mean, obviously it's open to interpretation, but when you look into it, there's really not a lot of chance of life on these planets for one reason or another. And I think this is a very exciting science because it shows us that our Earth is actually more unique than we originally thought. And there is some amazing design features of the Earth that allow us to live there. And to happen by chance would be, it just doesn't seem possible that a lot of these things could happen by chance. Yeah.
Now, Scott, of course, we've all read about, or many of us have anyway, read about Earth 2.0. It's in a book that I have. It's actually called the Bible.
Yes.
they talk about Earth 2.0, which we're not going to see for a little while yet, apparently.
Well, it depends. I guess depends when Jesus comes back, and then, there's depending on how you interpret end times, there's a millennial reign, and then you get the Earth 2.0. But the Earth 2.0 that God promises us is far beyond what any exoplanet we could find, or Earth 2.0 the secular scientists are trying to find, which is great news for us because we've got something really good to look forward to. We've got an Earth without sin, sickness, disease, suffering, where Jesus will be with us. He will rule and reign with us. And so that's a really exciting thing to look forward to. And I guess maybe that is part of the hope, part of the drive of finding a number of these exoplanets is, maybe we'll find, something that could be our home in the future. I know that's certainly what Elon Musk thinks about Mars. If we can become a multi-planet species, he says, then, that will give us extra hope. Because if we're only on one planet, then life might go extinct on one planet. And then if we've got another planet, then that would be a thing to aim for. But as believers, we know that we've got a much better hope because really these even the planets we know a lot more about within our solar system, they're very dry and barren. Some of them are ice worlds. Some of them are have no atmosphere. You think about Venus, one of our closest neighbors, that has temperatures in excess of 300 Celsius. It's hot enough to melt lead on the surface of Venus. It rains acid rain. There's really not very habitable places. that are around us. And even these exoplanets that they're finding now, and I should probably define that term because maybe not everyone's heard of it. So all exoplanet means is it means it's a planet that orbits another star. So that it's not in our solar system, and it orbits another star. And we've actually only known that they were real and they were out there since 1995. It's a rather recent phenomena. And that's why we get excited when we find new ones. And the James Webb Space Telescope in particular was able to give us greater insight into exoplanets because of its infrared capabilities. Unlike the Hubble Space Telescope, it's able to see larger wavelengths of lower frequencies. And that gives it some unique capabilities in looking at exoplanets, and specifically the atmospheres of exoplanets, because an atmosphere is a key. Depending on how close you are to your parent star, the atmosphere is another key parameter that needs to be just right for life, particularly liquid water to exist on the surface.
And how do they, is it like a spectrometer? They sort of look at it and go, okay, it's red, it must be this gas, or it's got these colours in it. How do they know what is there from here?
Yes, exactly. So what you're saying is correct. We split the light up into so there's a science called spectrometry, and you look through a spectrograph and you split the light up into different frequencies. And what I mean, this is how was a great breakthrough in the 20th century, was that we figured out that, well, on the Earth we can shine a light through certain molecules, and it will absorb certain wavelengths of light. And that gives you what you call a spectral signature. So all that means is there's certain frequencies of light that certain molecules absorb. So you could fill a chamber full of carbon dioxide gas and shine a light through it. And if you looked at the spectra, so that's the wavelengths of the light that are coming through. So you shine white light, which has got many different wavelengths in it. You shine that on one end of the box, and then on the other end of the box, you see which wavelengths are missing. And they're the ones that have been absorbed by the CO2 gas. So in the same way, we can look at CO2, oxygen, water vapor, different types of molecules in the atmospheres of exoplanets through this same technique. It's actually very difficult with exoplanets. It's being done a lot with stars, and the atmospheres of stars have been, and even the contents of stars have been inferred through by splitting the light into these different wavelengths. Yep. But it's very difficult with exoplanets because the exoplanet doesn't have its own source of light. You don't have, if you go back to the example I was saying in the lab where you have a box and you fill it with gas and you have a light one end, well, that works very well for stars because you've got a source of light. With an exoplanet, there isn't the light at the other end, and you're actually relying on the star's light to pass through the exoplanet's atmosphere. Yep. And that's why it's a bit more of a difficult science. And that's why these very powerful telescopes like the James Webb Space Telescope and the Hubble Space Telescope are needed to look at exoplanet atmospheres. And we're having some limited success in that.
But still, they haven't found anything that could possibly have life.
No. And there's been some really nice discoveries in finding these different molecules that could be a signature for life on these exoplanets, and often you'll see that talked about a lot in the media. But one of the key things is, if we're going to have life, well, we need a rocky planet. If you think about the planets in our solar system, we've got the inner planets like Mars, Venus, Earth, they're all rocky, Mercury, rocky planets, and they've got a solid surface. But then as soon as we get to Jupiter and Neptune and Saturn, if you think about them, well, they're gas giant planets. So they don't have a solid surface. So that's not very useful for life, especially intelligent life. Maybe you get some microbes that could fly about. So you need a rocky planet to start with. And the other thing you need is, they call this thing the habitable zone. And all that means, it doesn't mean it's habitable. It just means it's the right distance away from the star for liquid water to exist on the surface. Yep. Now, so we've found plenty of exoplanets in the habitable zone, and we've even found rocky planets within the habitable zone. But you're only talking in the numbers of tens now, finding rocky planets in the habitable zone. But to detect the atmosphere of a rocky planet in the habitable zone is very difficult because it's close to its parent star, and therefore you can't look at its atmosphere very easily. And it probably has a very thin atmosphere because it's a rocky planet. It's only the big giant planets that you can see the atmospheres on. So when you consider all the habitability requirements, we're nowhere near finding signs of life. But what we have found is different molecules on these in the atmospheres of these gas giant planets, which of course couldn't harbour life. And these molecules can be made from abartic processes, which just means non-biological processes.
Yes.
So there's nothing definitive saying this has certainly come from a biological, this chemical has come from a biological process. But that's the goal that they're looking for, is can we find these spectral signatures that indicate that there's these molecules that could only be produced by life. And we've not found that yet.
All right. Well, Scott, we're pretty much at our time's end. So again, why is it important, or why is it so interesting to the CMI guys that, other planets don't have life?
Yeah, so I think this is really interesting, because a lot of one of the big thing is, so the idea of ET and intelligent extraterrestrial life is becoming more popular now than ever, and it's just rose in popularity, especially we're looking mainly from the 60s till now. And 60s is when evolution was taught in all schools. And if evolution is true, then we're here by random accident. And if we're here by random accident, there must have been another random accident that happened somewhere else in the universe that also produced intelligent life. And really, that's where the idea comes from.
Yeah.
But the truth is, when we look at the exoplanets, we see they're so different from Earth. They're very barren, dry. Some of them are ice worlds, as I say. They look nothing like the Earth. And when we see that the Earth is specially created and designed, and as we compare it to these exoplanets, we see that more. And that just shows us that the Bible is true, that God has made the Earth for mankind, and he's made space and the planets and all the other stars for us to look at and to reflect how big and how glorious he is.
Yes, absolutely. Wow. Thank you, Scott. Another awesome week, and it's been a long time since we spoke to you last, and hopefully it won't be so long till we speak to you again next time.
That'd be good. Yeah, it's been great being with you, mate. I've enjoyed it.
Yeah, well, it's been awesome having you, and I thank you so much for today. I hope you have an awesome Christmas, and we look forward to the next time we speak. Thank you, Scott.